when I was invited, I started to think about what could be the topic of my talk, because I didn't have so many things to talk about related to ISS. And then I thought that maybe I could talk about a notion that is, reminiscent to ISS for finite state systems, and give some insight to the ISS community on the work that we are trying to do in that direction. Okay, so let me first give the context of this work. So the work that I'm going to present, it's motivated by symbolic control, which is a control technique that I've been working on for more than a decade now. It's a computational approach to controller synthesis, and it's fairly general. It can be applied to nonlinear systems, and it handles constraints on states and inputs. And the main idea of the symbolic control approach is to use finite state abstraction of a system. So essentially, when you do symbolic control, you start from a model, which can be a continuous or a hybrid model. Well, it's simpler if it's a discrete time model, but it can be continuous time. But let's say we have a discrete time model here. And the first step of the symbolic control approach will be to go from the continuous domain to the symbolic one. That is, we want to go from a continuous state, continuous input system to a finite state, finite input system. And so we go from classical dynamical system to finite state ones. Then once we have this symbolic model, we're going to synthesize a controller using this model. And what makes symbolic control powerful is that for discrete controller synthesis, we have many algorithms that allow us to synthesize controllers with mathematical guarantees for various types of specifications, such as safety, reachability, or more complex objective, like temporal logic. Then once we get a controller for our symbolic model, we get a last step, which is mapping back the control strategy that we synthesized in the symbolic domain to the continuous domain, such that we can actually control our original system with the controller that we just synthesized. So the symbolic control approach, it's a rich research area, and yeah. So one of the strengths is that it's applicable to a variety of nonlinear systems, and comes with guarantees of correctness of the synthesized control. Now, so symbolic control also allows to handle disturbances for system, and usually we deal with bounded disturbances. And I wanted to know if we could actually give a bit more than just robustness guarantees with bounded disturbance. Could we, for instance, guarantee that the deviation of the behavior of the system with respect to the nominal behavior degrades gracefully with the amplitude of the disturbance in the ISS sense in some way, right? So this was the context and the motivation for this work. So in the following, I'm really going to focus on this part, right? So I'm not going to talk about how we go from continuous to symbolic and how we go from symbolic to continuous, but I'm going to focus on this discrete controller synthesis part. But at the end of the talk, I will show some application to symbolic control. So the outline of my talk will be the following. So I will start by introducing some control problem that can be seen as some notion of input to state stability for finite state systems. So I will first introduce the notion of finite state systems and also the notion of controller that we are going to consider, and then define the notion of gain for controllers and show that we can try to optimize this gain. Then in the second part of my talk, I will talk about computation, right? In the first part, I define a control problem and show that there exists a solution. The second part of my talk is more related to, can we design an algorithm to compute this solution? And I will show an algorithm that gives, that provides the solution to the problem. In some cases, it's not working all the time, but I will explain that in more detail later. And the third part of my talk will be related to the application of this approach to in symbolic control, and I will show an example in adaptive cruise control. Okay, so let's start to give formal definitions. So in the talk, I will consider finite state systems, and the systems that I will consider, they are of this form, right? So I have, you have essentially a difference inclusion, right? So xt plus 1 belongs to some set which depends on xt, ut, and alpha t here. So here the system, in the system, xt is the state of the system. As usual, I use the same notation as classical notation. Let's say the main difference with let's say classical system is that here we have only a finite number of possible values for x, right? So x of t can belong to a subset, a finite subset of integers, for instance. Similarly, ut is the input, and it can also take a finite number of possible values. And then we consider system with disturbances, and I denote the disturbance with alpha t here. And it's also finite, and here I will assume that we have an ordered set of disturbance, right? So the disturbance, it can take value from 0 to n, where n is an integer. Then we have the dynamics of the system, and you can see that the dynamics is non-deterministic, right? Here it's not an equality, it's we deal with set-valued maps. And we're going to assume that the set-valued maps, so the transition map, they satisfy some monotonicity property with respect to the disturbance, that for all state and inputs, x and u, the set of successors for a given disturbance alpha is a subset of the disturbance of the successor at the next disturbance level for disturbance alpha plus 1. So intuitively, this means that this assumption is that larger disturbances, if you consider larger disturbances in your system, this produce more non-determinism, right? So if you want to get an intuition why we make this assumption and what can be represented with that assumption, imagine that here you have an equation, and it's not an inclusion, but it's x t plus 1 equal to f of x, u, and w, where w is a disturbance, is a vector. Then you can define f alpha x u as the set of fx u w, such that the norm of the disturbance is less than alpha, right? So this, if you embed this system in this set-valued map, then this set-valued map will satisfy this monotonicity property here. So it's a quite natural property to assume for the disturbance. Okay, so here you have an example of such a finite state system where we have a system with 3 different states, 0, 1, and 2, and two different input values, A and B. And then you can see the transition relation that is represented by the edges on this graph, right? So for instance, here, from input 0, from state 0, if I apply input B, then I will move to state 1. Right, so that's essentially how you can understand this description of the system. And then we have two types of edges. So here it's the case where we have n equal 1, so meaning we have only two levels of disturbances, 0 and 1. And here, so the plane edges represent the low level disturbances, right? So this is the nominal behavior. And the dashed edges, they represent the transitions, the additional transition that we get for higher disturbances. Right? Okay, so that's the type of system that we will consider. And now we're going to deal with controllers, and the controllers that we will consider are also set-valued controllers. So it's a map from the state to a set of inputs. And when I have a controller, I can define the closed loop behavior of my system as follows, right? So you given x of t, you pick any input in C of x of t, and then you move to one of the successors. So in this example here, which is the same as the one on the previous slide, for instance, if you consider, you can consider, for instance, two different controllers. The first controller is a controller that picks input A always, right, from any state. And then this is the closed loop behavior. So basically, we remove all the states, all the transitions that are labeled by the input B, right? And this system is the closed loop system for the controller that always outputs B, right? So of course, there are many other possible control strategies, but here you have two examples of two particular examples of controllers, and here are the closed loop behaviors that we get for this controller. Okay, so now we have systems and we have controllers. And I'm going to define the notion of control gain for these controllers. So I'm going to consider that I have a cost function on the states of my system. So it's a function from the state to the positive reals. And then I will consider functions that are gain functions and that are non-decreasing functions from the set of disturbances to the positive reals. So now I consider the following definition. So let's say I have a controller C. So function gamma C is a control gain for my controller if there is a set of initial states and a time bound such that for all the closed loop trajectories starting in the set of initial states, after the time bound, then the cost h of x of t will be bounded by gamma c, so the control gain evaluated on the maximum disturbance over a bounded time interval. Right? So here I take the maximum of alpha s on a time interval of length tc. Right. So if you look at this definition, this looks for people working with ISS, I guess this looks very familiar to most of you. And the control gains, they are reminiscent of ISS-gain stability theory, and they allow to quantify to show two things. First, that if you have small disturbance, then you have small deviations in the nominal behavior, right? You can relate the cost to the amplitude of the disturbance, and higher disturbances will result in higher costs. And you also have the fact that if you have a sporadic disturbance, and that if a disturbance disappears at some point, then after some time, here after TC time unit, then you will restore the nominal behavior, right? So this is very similar to ISS in some sense. I mean, we can say that this is like finite time ISS, right? Because this has to be, it's not an asymptotic gain, but it's a gain that we reach in finite time. But you have to realize that we are working with finite state systems, and in finite state systems, finite time stability and asymptotic stability, they are just two equivalent notions. So any system that is asymptotically stable is also finite time stable for finite state systems. So this is the reason why here we only consider the finite time version. Okay, so given a controller, I can get a control gain for that controller. And now I'm going to see if I can synthesize a controller that somehow optimizes this gain, right? I want to have a gain that is as small as possible. So what does it mean to have a gain as small as possible for a gain is a function. So to define what is the notion of optimal gains, we're going to define orders on the set of gain functions. And we're going to assume that we have a total preorder. So which means that we are able to compare any pairs of gain functions. And we're going to assume, make this natural assumption that if we have a gain function that for all k is smaller, gamma 1 of k is smaller than gamma 2 of k, then for our preorder, the specific one that we consider, will get gamma 1 smaller than gamma 2. So examples of such preorders, I give 3, but you can imagine like many of these. It's actually easy to come up with many of such orders. We have the lexicographic order, which is defined as follows. So gamma 1 is less than gamma 2 if basically they, well, you start by comparing gamma 1, 0 to gamma 2, 0. Right? If gamma 1, 0 is smaller than gamma 2, 0, then gamma 1 is smaller than gamma 2 in the lexicographic order. Then if gamma 1, 0 is equal to gamma 2, 0, then you go to gamma 1, 1 and gamma 2, 1, and so on. So you compare starting from the gain at 0 and go with increasing disturbances. Then you have the colexicographic order, which is the other the similar notion, but in the other direction. You start comparing the gains at the maximal level of disturbance, so gamma 1 of n. And so if gamma 1 n is strictly less than gamma 2 n, then you're done. If they are equal, then you go to gamma 1 n minus 1 and so on. You can also define for instance, the summation preorder, where gamma 1 is less than gamma 2 if the sum of the gains at all values is less than the sum of the gains of gamma 2. And well, essentially, you can also define similarly to the summation preorder. You can imagine that take any monotone function of n plus 1 dimensional vector, and then f of gamma 1 less than f of gamma 2, you check this condition, and that gives you another preorder. So you can define many preorders like this. So just to make it a bit more concrete, this is what we get for like the three orders that I defined here. So here you have three examples of gain functions. And when you consider the lexicographic order, you're going to start from the minimal disturbance, and you look at the one that is you know, the lowest one. So in the lexicographic order, gamma 1 is the smallest one because it's the at alpha it's the one that starts the lowest, right? And then it's gamma 3, and then it's gamma 2, right? So this is the ordering that you get for the lexicographic order. If you consider the colexicographic order, then you have a different ordering, right? Because you start from here, and here you see that gamma 2 is less than gamma 3, less than gamma 1, right? So in that case, we get this, this ordering for this colexicographic order. Then if you look at the summation order, we have so basically the summation order selects the gain where you have the smallest integral, right, below the curve here. And in that particular example, that would be gamma 3, which has the smallest integral, then gamma 1, and then gamma 2, right? So that would be what you get for that gain. Okay, so once you have a pre-order, a total pre-order on the gain functions, then you can compare the gains of different controllers. And then you're going to say that your controller is gain optimal if it has a control gain gamma C, such that for any other controller C prime, with control gain gamma C prime, gamma C will be less than gamma C prime. Right, so you want to compute a controller that has the minimal gain function for a given order on the gain function. And we can show the following result is that for any total pre-order on these on the gain functions, and the pre-order has to satisfy this assumption here. So for any total pre-order satisfying this assumption, then you can show that there exists gain optimal controllers. It may not be unique that there exist gain optimal controllers. So it makes sense, right, to try to compute such controllers. So of course, if you choose different pre-orders, you have different gain optimal controllers, right? The pre-order has an impact on the controller that is optimal for that order. And for instance, if you consider the lexicographic order, then you're going to optimize the nominal behavior first, right? If you consider the colexicographic order, then you're going to optimize the worst case behavior first. So depending on what is your primary control objective, then you can select the pre-order that is the most suitable. Okay, let's go back to our example where we have these systems and we have two different controllers. And if we compute the control gains for these two controllers, for instance, if we look at this one, so when we have the low-level disturbance, so the low-level disturbance, they are the plane edges, right? So you remove these dashed edges. So you can see that when we only have low-level disturbance, we go to the state 0 here, right? So here the control gain for the low-level disturbance is 0. And when we have disturbance, right, so we add these dashed edges, and we can see that now the gain is 2, right? So we get 0, 2 in that case. And for that controller, well, we can see that here actually the disturbance has no effect on that controller because we only have plain edges. And here in that case, the gain function, well, we can see that we end up in this state here. So it would be 1, 1, right? For low-level disturbance and high-level disturbance. So, and we can show that actually this, the controller that outputs always A is gain optimal for the lexicographic order, right? It's so it optimized the nominal cost, while CB is gain optimal for the lexicographic order, right? So it optimized the worst case behavior. But now if we look at the summation order, then they are both actually gain optimal, right? Because here you can check that the sum of the two values are equal. And so if you consider the summation order, then these two controllers are just as good as far as this order is concerned. Okay, so this is the first part of the presentation, and I presented the control problem that I'm interested in, right? So I have a finite state system. I have a notion of an order on gain function, and I want to synthesize the optimal controller for that particular order. So now I'm going to show how we can try to synthesize such optimal controllers. And to make the presentation simpler, I will consider a particular case, a particular setting. So I have a system, and right now I'm just going to consider the case where we have two levels of disturbances. So we have the nominal system, which is for alpha equals 0, and we have the disturbed system for alpha equals 1, right? And we have F0, which is included in F1. And we're going to focus on the co-lexicographic order, so meaning that we want to optimize the worst case behavior first, and then when we achieve the optimal worst case behavior, then we want to optimize also the nominal behavior. But the primary objective is to minimize the worst case behavior. So we're going to have a two-step approach to solve that problem. So the primary objective, as I mentioned, is to minimize this value here. And to do that, we're going to solve two dynamic programming problems. So we are first going to compute the fixed point of that dynamic programming iteration. And if you want to get some intuition of what this program computes here, you can see that the fixed point here, it satisfies some control Lyapunov type of condition, right? That there exists an input such that the value at the successor is no greater than the current value, right? So I can guarantee that by selecting correctly the control input, I can make this function non-increasing, and also this function is an upper bound on the cost, right? So basically, this will allow me to provide a bound on the future cost that I can get. And so this is when I compute this function is for the worst case disturbance here. And then I have a second dynamic program iteration that I want to solve, where I use basically the output of the first problem here as input. And then I solve this iteration here, which looks similar to the previous one, but it's not, it's not max here, but it's the minimum here. And essentially what this program does, W1 star of X, it basically gives me what is the minimal value of V1 star that I can reach by selecting correctly my control inputs. So I do these two steps here, and basically when you have these two functions, this W1 star and V1 star, right? Then you can define a controller and two sets. Basically, this set here is going to be, well, let's start with this one. So x infinity is going to be the attractor of my system. So here it's, the trajectory will end in this set and stay there forever. And x0 will be the basin of attraction. And essentially, I have a controller here, which when I'm in the attractor, I select an input that keeps me in the attractor. And when I'm in the basin of attraction, I select an input that makes me move towards the attractor. So what I can show is that for any controller that is gain optimal, the gain, the value of the gain function for alpha equal 1 will be the same as for this controller C1. And moreover, the set of initial states that are controllable for my system, they will be a subset of the initial states. The basin of attraction will be included in the basin of attraction of this controller. And even more important, in the attractor, the set of inputs that is given by the gain optimal controller will be a subset of the control inputs that are given by this controller. So I will use that later, but for now, let me somehow just explain what we do. So we have the two functions, W1 and V1. So V1 is going to allow us to compute what is the smallest attractor that I can get, right? And this is this blue region, right? And then once I have the smallest possible attractor, I have I can compute the yellow region, which is the basin of attraction for my control. Okay, so we optimized the worst case behavior, and we know that we are optimal. So now, once we optimize the worst case behavior, we still have some freedom for some design, right? Because we have set valued controllers. And you can see that C1x is, in particular, in the attractor. C1x is a set, and I know that the gain optimal controller will be a subset of that C1 of x. So the main idea is going to try to refine inside the attractor this controller to try to reach the gain optimal controller. So basically, what I'm going to do is that I'm going to refine the controller to try to minimize, so inside the attractor, to try to minimize the gain for the nominal behavior. And to do this, essentially, I have a similar dynamic programming iteration that I need to solve, right? So here, this will allow me to compute the smallest possible attractor for my nominal system. But what you can see here is that I constrain the choice of inputs to be an input that is given by the controller C1 that I designed for the worst case behavior. So by doing this, I guarantee that I maintain the guarantees that I had for the previous control. And I also compute the W0 here that allow me to compute the basin of attraction to that minimal attractor. And similarly, I can define my controller. And what you can see is that the controller that I get, C0 of x, it's always it's a subset of C1, right? Because outside the attractor for the worst case disturbance, I provide C1, and in the other cases, it's a subset of C1. So, well, what I can show is that this controller here, C0, I can compute the control gain of this controller, and it's given by beta 1 and beta 0, which are computed from the functions here that I get from the dynamic program. And then what I can show also that this controller here, C0, is again optimal controller if I have this condition here, which is that if the function W0 star, which I computed on the previous slide, is basically constant on the attractor x infinity C. So that may not be always the case. So if this is not the case, I cannot guarantee that it's gain optimal. But if this is satisfied, then I know that it's gain optimal. So to try to give a geometric intuition of what we are trying to do. So in the first step, right, we designed a controller that allows to, from any state in the yellow region, we drive the trajectory to that blue region, and we stay in that blue region forever if the disturbance is at the highest level. And in the second step, what we did is that we computed this red region here. And what we guarantee is that if at some point the disturbance comes at the lowest level, then the trajectory is going to enter in that red region and stays there as long as the disturbance stays at the zero level. And then if the disturbance goes back to the first level, then we might exit this red region, but we know that we're never going to exit this blue region. Right? So essentially, we have a nested sequence of attractors, and we know that each attractor corresponding to a given level of disturbance. And the dynamic programming that we do allows us to guarantee that the attractor that we compute, they are the attractors that correspond to the minimal cost, right? Attractors of minimal size for our system. So this is how we try to optimize this gain function. Okay, so just some simple remarks. So as I said, it's an incomplete result, but I think that even when the optimality condition is not satisfied, it remains a useful result. Why is that? Well, first, when we use that approach, we guarantee that the controller that we get the optimal behavior when we have high-level disturbances, right? So the gain function of our controller evaluated at 1, right? So at the high level of disturbance, this is the minimal value that can be achieved by any controller. So we know that this is the best we can do. And even if we are not, optimal in the second step, we still have what the work that we do allows us to improve the behavior of the closed loop system, and because we get that the gain of C0, so the controller that we get after the first step, is smaller than the gain of the controller after the first step. So in general, it's strictly smaller. There might be cases where this is equal, but what I would like to say that in any case, you don't degrade the behavior of your controller. Okay, so here I believe the algorithm that I presented is already quite complex, and so I didn't want to present the full version for the case where we have more than 2 levels of disturbances. But the approach can be extended to that case, and if you want to know more, then you can just check the paper that presents this method. Okay, so to end my presentation now, I'm going to show the type of controllers that we can synthesize by using this approach. So I'm going to consider an adaptive cruise control problem. So I have two cars, and the variable of so the different variables are the distance between the cars, the velocity of the follower, the velocity of the leader. I define also the time headway, which is the distance between the cars divided by the velocity of the follower. So basically, it's the time that will take to the follower to reach the current position of the leader. And then we have the dynamics of the system, where so the distance is the derivative of the distance is the difference of the velocities, and then the derivative of the acceleration of the follower is given by this equation, where u is the control input. So we control the follower, and we have some nonlinear term here. And then we have the leader that has that also has a dynamics, and with an input W that here is considered as a disturbance. And essentially the dynamics of V2 it's like an integrator that saturates between the two bounds, right? Maximal and minimal velocity. So we want to control that system, and so we actually want to control a discrete time version of the system. So we first do some time discretization, and then we want to solve the following problem. So the specification is the following. We want either to keep the time headway to greater than some critical value. And if the time headway is greater than this, then we want to maintain the velocity V1 so of the follower at some reference value. So basically, essentially, when we are far from the leader, we want to maintain some reference velocity. And the second case is if we are close to the vehicle, then we can reduce our velocity below the reference velocity, and what the objective then becomes to maintain the time headway to the desired value, right? So to achieve the specification, we can basically define a cost function, which would be the distance to that particular set, right? So this is the cost function that we consider here. And so we want to synthesize a controller that is going to stabilize this set. And we want to get, because we have disturbance, we are not going to be able to stabilize exactly and to go to that set asymptotically. But we want to have a controller that has minimal control gains, right? So we want to get some optimal controller in this way. So to do that, we're going to use the symbolic control approach. So we use the symbolic control, and we somehow go from our continuous system to a discrete one by discretizing states and inputs. So we have a partition, and then we analyze the possible transitions between elements of the partition. And basically, this gives us a finite state model. And we're going to use that finite state model to compute a gain optimal control. This is the type of controller that we get. So here, just to mention, so when we do symbolic control, so we have to go from the continuous to the finite state, right? So here we partition the state space in 60,000 regions with 20 input values and 3 disturbance level. And to go from the continuous to the discrete, it takes like 42 seconds. And then we have to optimize right? So basically we have to solve, because we have 3 levels of disturbance, we have to solve like 6 dynamic programming problems, and this takes some time. And in this case, it takes 93, well, 1 hour and a half to basically compute the controller. And here you can see the gains that we get for the different level of disturbances. So here on the figure, you can, this is the attractors and the basin of attraction that we get. So basically, the red region is the sets that we try to stabilize. So we try to come as close as possible to that red region here, right? So this is you have to imagine that this is in 3 dimensions, right? So this is 2 slices of this 3-dimensional region. And then we have the attractors. So the white attractor is the one for the lowest level of disturbance. Gray, light gray is the middle level, and here a bit darker, it's the attractor for the highest level of disturbance. And the dark gray region here is the basin of attraction, right? And what is black is what is outside the basin of attraction. So basically, in the black region, the follower would crash in the leader. Yeah. Okay. So that's we have these different regions, and now showing a simulation. We consider a scenario where so we have the leader that drives at velocity 20 meters per second initially, then it slows down, then it accelerates, slows down again, and accelerates again. So if you look at the input, right, the disturbance, this is the level of disturbance, right? So you have low level, then high level, then low level, medium level, and so on. So this is the cost function, the cost that we observe using the controller. So either using a controller that only optimize the worst case behavior, and this is the cost that we get for this is the blue curve. So we can see that okay, we get some value here that is constant and does not adapt to the level of the disturbance. And if we have tried to use our approach to optimize all the gains, right, the gain function, then we get a controller that is able to, the worst case behavior is pretty similar, right? So the cost function here is almost the same as for the blue controller. But when the disturbance is low, then we get a much better behavior. And this is what we see on the figures here. Here you have the time headway and the velocity, and we can see that with the gain optimal controller, we can basically track correctly the objective, right? So initially we track the velocity, then we get too close to the vehicle, so we now track the time headway, and then the distance increase again, then we track the velocity, and so on. So this is the type of behavior that we observe. Okay, so now time to conclude. So the contributions of this work. So first we propose, we formulate a control problem, right? An optimal control problem, which is that of synthesizing controllers that achieve optimal gains. So we showed that such controllers exist. I mean, the existence result is valid only for finite state system. The question is open for other type of systems. Then we provide algorithm to synthesize such controllers. We have an incomplete solution, and we try to make advances on the complete solution, but it's not that simple. And we showed an application to continuous synthesis using symbolic control. So the type of perspectives and the future work that can be addressed. So For now, we only have an algorithm for the co-lexicographic order, but as I mentioned, you can define gain optimal controllers for any orders, right? So can we synthesize such controllers for other orders? And what would be nice is to have like some generic solution that works for all the orders. And this is not specific to a given order, because that would be much nicer to have a general solution. And yeah, as I mentioned, the question for infinite state system is largely open. My feeling is that the existence of gain optimal controllers is it should be feasible under some technical assumptions, but then the synthesis problem, right now I don't really see how we can handle that. In particular, if we have like continuous level of disturbances, right? If alpha is not in a finite set but in a continuous set. Here we iterate on the values of alpha. So in the continuous domain, I don't know. So we would get some maybe PDs in alpha. But yeah, I think that would be very, very complex. So with that, I would like to thank you for your attention. And I would like to acknowledge the contributions of my former postdocs who worked on this topic. And if you want to know more on that, well, you can read the following papers where the theory is presented. Thank you for your attention.